All right, so yeah, this is going to be section 36, right? Section 36, support vector machines. So at this point, we would have gone through a few machine learning algorithms, all supervised learning. So we went over section 33 was, I believe, correct me if I'm wrong, decision trees. And then, is that all right? What's section 33? Is it, am I wrong on that? I know one of them is decision tree, either 34.
Nearest neighbors.
Thank you. So k-nearest neighbors is the first one for section 33. Then we had decision trees for 34. Section 35 was ensemble methods, which is like random forest, for example, which basically will usually use multiple algorithms together. And then we actually have support vector machines for section 36. So these are all supervised learning. Remember that it's all about what's it called? Having classified data. So your data is already pre-labeled. And basically you're using those labels to learn / train on that data. Okay, so I'm gonna go ahead and start sharing my screen so we can talk about support vector machines. And some quick things about support vector machines while I'm sharing my screen. They are, what's it called? They were very popular like in the 90s, which sounds kind of like they're old, but they're very powerful. They do rely on a lot of using gradient descent, for example, actually optimizing and stuff like that, which we have a lot better now with, what's it called, with GPUs and stuff like this in different architectures. So they're still very, very powerful. They're very, very popular. There's a few reasons why we actually like them. So we'll get right into that. And note that these notebooks I will go over, support vector machine intro and kernel trick, those should be on the resources page, or not resources, well, they'll be on the repo page that I keep all the notebooks in under machine learning, so you'll find them there. Okay, so I'm just kind of importing this right here and we'll get right into it. So this is like just a classic shirt where it's like, I support vector machines, which I just found this little image on Amazon. So why are support vector machines cool? Basically, it's another, like I said, supervised learning technique to classify data. And what's really cool about them is that we can actually decide on sacrificing our accuracy to get better boundaries between decision points and stuff like this. So let me ask you guys, why would it be like useful? Like you might say like, oh, this is really cool because we can sacrifice accuracy, but why would we want to have a better defined boundary over accuracy? Because you might have something where it's like either similar accuracy or even worse accuracy, but a better boundary. Why might we care about this? You think of some ideas? So maybe I can give you guys a hint a little bit, right? Is that, for example, on this t-shirt right here, on this guy's t-shirt, if I drew a line that was like this, in this red, that accuracy is 100%, right? Like I am getting all the red on one side, all the green on the other side, right? However, if I drew a line that's kind of close to that black one in blue, I don't know if you guys can see that too well. Okay, if I do that one, that also is classifying everything the same way, right? All the reds are on one side, all the greens are on the other side, right? Okay. By nature, what would you say is the better one?
The blue?
The blue one. And why might you say the blue one, Adam?
It's directly in between all the red and the green dots.
Yeah, it seems like this red one might be assuming too much, right? Like it's kind of like it technically splits it through, but that blue one's more realistic on what we see on the data. So that's one reason, and I'm going to show you an example of that one. Another kind of like example of this, of like why the boundary might matter, is imagine if you have a boundary that went like this. Okay, and that's accurate, right? That's like you can imagine it's going on the other side. All the green sides are on one, all the red sides are on another point. But you probably instinctively know like that's not a good model. Like you're like, because we're overfitting essentially, right? We're making it too precise. Like if there was a new data point, like in the middle right here, okay, what would that be labeled at? Would that be labeled as the red on the top side or the green as the bottom side?
The green.
green, right? So yeah, so we would make mistakes because probably it'd make more sense, like, you know, from k nearest neighbors, it probably would make sense that these should actually be grouped together. So we can actually sacrifice accuracy and say, well, you know what, if we had a model, or a model that basically had a better boundary, but maybe sacrifice some accuracy, we'd be okay with that because you're able to generalize better. And that's why support vector machines are really good, because you can actually kind of specify that. So let's see a little bit of what this would look like. So we're going to look at these little lines right here. So just kind of walking through this code. I'm trying to do a little more code so you guys can see this. This data set comes from sklearn. So you can see I imported it way up here. Okay. So they're just from sklearn data sets. So it's nice is that it's nice that some packages actually have data is already built into it. So we don't have to like get a CSV. So you'll see me use this a lot. So I'm just loading iris data, which is actually basically it's about different flowers and stuff like this. And so they have things like features like petal length and like, you know, all these other like technical parts of the flower. I think it's about 550-ish data points. I could be wrong, actually, it might be less than that, but it's not that many data points. But what I'm doing here is basically loading in the data. And so I'm going to split this right here so you can see it. So I load in this data and you'll see that all of the iris right here, if I put in type, have you guys seen iris yet? I'm not familiar if I've shown you guys this, this data set. So you can see here I have, it's a different type. If I actually print out iris, you'll see. So first of all, it's a bunch, which is a specific class for sklearn. But if I print out iris, you'll see it looks a lot like a dictionary. Basically, I have a data here, right here. And then underneath here, you actually see there's targets. So basically the classification, what this label is, there's 0, 1, 2, basically the different kind of targets you can have. And there's some extra information like the target names. So you can see here basically some information about what those different are. I think there's also like data, like feature names, which I'm not sure exactly where it's on here. But if I do like feature names, here it is. You can see here sepal length, sepal width, petal length, petal width. I don't know what a sepal is exactly. I'm no biologist. But the point is that you can get this whole data here. So we're going to look at specifically, split it up into basically just two parts. So this is actually a really useful function, np.where. And this np.where function basically will take in a numpy array, which is what target is, okay, to basically compare across saying, is that target a 0? And if it is a 0, we're just going to keep it as a label of 0. Otherwise, we're going to label it as a 1. This is basically just to remove, so I only have to worry about two different classifications to make it a little bit easier for us. Okay, so that's what this part is. The second part here is just plotting it out so I can see, and I'm looking at just the second feature. So we notice that there's 4 different features here, right? So basically, I'm just plotting out one feature, so feature 2, so this column right here, versus column 1. So I just put it so we can do this, and I'm using the color as target. So basically, there should be 2 different colors. Okay, so if I do this now, and I plot this out, you can see here, those are the 2 different colors going on. So we can see is that basically here's target, let's say 0, and this is target 1, okay? And these are the different features, X and Y. So you can see there's definitely a group between these 2, right? Okay, so I just wanted to show you guys that this is obviously not about support vector machines yet, but the idea here is going to the next question. So as I kind of hinted up above, if I go ahead and run this guy right here, we can see I have basically made 2 like fake models, line 1 and line 2. So you see this blue line here and this orange line going here. And kind of like what Adam said, which line would be better, a better model based on just instinctively.
Is it the orange?
Yeah, the orange one, right? And that's similar to like what you had said, Adam, right? Is that it makes sense that the orange one is a better model, at least, you know, from what we can see. And kind of, can you reiterate like what the reason why this would be a better model? Like why choose orange over blue?
I chose it because they seem like there's an equal amount of empty space between the dots and the line.
Yeah, honestly, that's essentially what support vector machines are doing. They're trying to make that space equal and make it honestly as big as possible. If I had another line, like if I draw in like purple here, if I drew a line that was like this, oops, I should actually draw, come on there we go. If I drew a line that was kind of like this, right, it still classifies the same, but you can see here, it's like, well, you probably instinctively know it really shouldn't be this. It really should be off to the side, more in the middle. And that's essentially what support vector machines are doing. They're trying to make not just good classifications, but also make good boundaries. Okay? And we'll talk about what this white space is. Basically, it's the margin, which, you know, kind of makes sense, hopefully, with when we say margin. So to iterate kind of, it's that actually isn't everything. It's not just important just to get the right data points. We want to make sure that our boundaries are also important. So like I talked about, like overfitting, we want to make sure that we fit it so those data points don't overlap in a lot of, not data points, sorry. The boundaries have a more natural and understandable boundary. Now you can still have a boundary that kind of loops in a little bit, but you don't want something where it's like purposely trying to fit between each of the little points. Or like, you know, for example, I would even say this blue line is actually overfitting. It's basically, even though it fits across it, you would actually say, well, the thing is that this technically works, but if I had a point over here, I would actually say that's probably a yellow point versus a purple point because it's more similar to these yellow points over here. It's basically assuming on the data saying that it's being overconfident on where it slices it. And that's what we mean by this overfitting aspect. Okay. So kind of like defining a better boundary. Adam, you kind of said one already, is that basically you just wanted that extra white space, right? It's like make the white space as equal as possible compared to like probably over here where it doesn't really make it white space. Anything else we can maybe think of like a better boundary? And just throw out ideas. There's no like right, wrong answer here. So maybe Ala, do you have an idea what maybe like would make a better boundary? Like what would be a bad boundary? Like maybe that's a good way to kind of answer this question.
The one that does not group items.
Yeah, so maybe like if you had a boundary like this, right? Like that would not be good, right? So yeah, we want to make sure the boundary still like fits the items, right? So good. Anything else we can think of? That might be, I kind of hinted at one. So would you want a boundary that would be curvy like this? Like, would you naturally want one that kind of fits in and out like this?
So like check for over or under fitting.
Yeah, right. Like, and these are just kind of like, we're just kind of using more words. Like, you know, what would like, if you saw this boundary as a person, would you say like, oh, that's not a good one? But yeah, that's be a case of overfitting, right? We don't want that we want that boundary to have a nice, as simple as possible without being too simple, right? And this is where support vector machines, you can adjust those parameters and make it fit better according to what you feel kind of deal. So yeah, cool. I think we hit, oh yeah, go ahead.
Sorry, would a boundary ever be like a semicircle?
Yeah, you could have something like that. So like when you say semicircle, do you mean like kind of like it wrapping around the data points?
Yeah, like a C, like
yeah.
the letter C kind of. Oh,
yeah,
okay.
So you might have something like this, right? Like,
yeah, exactly.
Yeah, definitely. You could have even data points, and we'll see this in with the kernel trick. We might actually see something where a boundary actually wraps the whole data point around like this. Because maybe, for example, you have data points that kind of like are out here down in purple. Mm-hmm. And like, so it's like that case, like, well, we really say these are all one group together. And these things on the side, well, this stuff is all like outside. That can also be a boundary as well. And in that case, you know, you still wouldn't want ones that are like really curvy, like within here, because that's overfitting, right? That's kind of being too precise along here. Okay. But yeah, good point. And we'll see some of those too. So yeah, basically a big one is just saying you want to see about how far away it is from the line, right? You kind of want that extra space, like Adam said. You don't want it to be curving in and out of the data points. You kind of want to be able to give a little extra like buffer, I imagine, right? And that's what we define it as, this margin. So just to kind of show you some margin again, this is very similar to what we had before. Basically just plot out the same exact graph that we had above right here, okay? And this time I'm gonna go ahead and draw out a line. So it's something to separate the points. And I'm gonna show something with a very small margin and something with a very large margin here. And basically really you have to know is that this small margin right here, actually really put this, that's large margin, but if, is that we're taking a line. So imagine this line, if I just go ahead and plot this out, maybe that'll be good. If I plot this out, you can see there's a line right here, right? And so we want to define this margin, like how much of a margin should we actually care about? And so we can see here is, if I do this right, I can go ahead and copy this, paste into here. We can define a margin as basically just being a little extra point. Basically, we're gonna extend the line outward a little bit. So I wrote it in like these dotted 2 dashes lines. So you can see here in orange, hopefully you guys can tell that difference right here, all right? But in the blue is our model, which is literally the same as this guy right here. And then in the orange, that's kind of our margin, our buffer, like how much buffer we want. And then we have our red margin right here, which is how much buffer. Which would you say is a better like margin? Like if you had to say like what's a better model when we say this margin of like how much buffer, do we want to consider that smaller buffer or that bigger buffer? Just based on what you see here.
The smaller.
Maybe smaller, right? So what's the reasoning that you might want to do a smaller buffer?
Just in case of future data points, it might go within the larger buffers.
Yeah, so maybe you do want a smaller margin to make it so you, just in case it does fit over through. There's a slight problem with this. If you make a smaller margin, you actually in a lot of ways are assuming that your model is actually really accurate, that model is actually going to really well represent this part. So what's going to happen is that, let's say you have data points like these purple ones that kind of go like, let's say, that kind of go like this. Oops, I need to draw on the side, like within this part right here, okay? Well, what's going to happen is that even though it's outside this margin, you're going to say, oh, I still have a really good data. I still have a really good line. Where in reality, maybe your line needs to be more at this angle right here. So what happens with this smaller margin, basically it means that like you're expecting your model to be more accurate. So actually with a larger margin, you're in a lot of ways, it sounds kind of weird, like kind of counterintuitive, I'm sure, but having that larger margin will allow us to count for these things that cross over this threshold. You're like, oh, wait, like my margin's not good. Maybe the model itself needs to be adjusted. And this is where we can basically use gradient descent to keep adjusting our model. Where if you had very small margins, it'd be hard to keep adjusting your model because your model thinks it's right every single time.
So the model would always only readjust itself if data points are within the margin. It doesn't really factor in points outside.
It does technically. Like what will happen is that, and we'll see this as we adjust like in C and stuff like that. But what happens is that if you can think of like the margin, it's like the standard deviation. If you think maybe that's not the best example, but like if you have very small margins, it basically, the error decreases as we go out further and further and further. So the problem is that if we have very small margins, like 4 margins without, so let's say it takes like 2 or 3 margins until it hits a point, those points won't matter as much because we'll go something like, like think of like R squared, like how we basically larger points away from us, those residuals don't matter as much compared to ones that are very close nearby. So that's essentially what's going on, is that by using, by having larger margins, we actually say, oh, like those errors will count more and they're easier for us to adjust with gradient descent. Okay. I know it seems like when I first heard this too, I feel like it's counterintuitive. Like you might say, oh, you want smaller margins to be safer, right? Like that's what makes sense. But in defense, we want our model to like be like, in a sense, like not overconfident, but basically like account for those big errors. Because then what happens is that if there is something in there, it's more likely to adjust. Where if the errors are really small, it's harder for us to realize that we need to readjust the model. And when I say we readjust, I mean gradient descent says, oh, the error is pretty big. We need to adjust it to make it smaller and smaller.
Can the margin ever include existing data points?
Yeah,
it's already
definitely.
there. Oh,
It probably will too, because like a lot of times this is a very nice data set, but a lot of times there's a crossover. Like sometimes the yellow is crossing over the purple, and sometimes the purple is crossing into the yellow, just because it's not completely defined. You can never, a lot of data sets, you can never find a perfectly defined level, but you can get something that's like, well, acceptable enough. And so that's where you can use the margin essentially to also say, well, how much should we care about the data points within here? Okay. Good question. All right, cool. So cool to move on then. Or any other questions, comments? No? Okay. So kind of leading here is like, where do we go from here? It's like, okay, we see these margins in here. I kind of reasoned out like, we need larger margins, right? So basically we will kind of do two different things for support vector machines. And like, this is where like, I can say like, it sounds super simple. Like I like to phrase things and it sounds like, well, that seems really obvious. But obviously you have to make the math work. And what's nice is that we don't have to do it from scratch. Usually we can use the package itself. But the main two things is we want to make sure, first of all, are we classifying the points, right? Like if we are making a model that goes like right through these data points, right? If I make let's see if we can do that right, there we go. If I make a model that goes straight through those data points, well, that's not going to be a good model, right? It's not going to explain it. So first of all, we need to make sure we do the right classification, right? But also we want to consider how bad our boundary is. Basically, how are we within that margin? And we want to make our margin as large as possible with making few mistakes. If we're too conservative and make our margin way too small, what's going to happen is that we're never going to know if we're wrong or not. It's kind of like not seeing, like, almost having blinders, like for what the model's like gradient descent going on. So we actually want to make it as big as possible, but still within like, some practical terms. You want to make it so big that you're counting points that are already in there if you don't have to. Okay. So this basically gives us this error function, our loss function, as essentially the error of classification plus the error of the actual margin itself. So basically you want to say, one, for error classification, does our model actually classify everything, or as best as it can? We want to minimize that part of the error. But also the other part of the error is how many points actually fall within that margin. And we'll talk about how we actually define that. But the important part is we're saying, okay, like we want to minimize both of these errors together. Okay. Everyone got me so far? Any questions? All right, awesome. So this is where, oops, I need my mouse back. Okay, this is where we'll go a little bit of math. So note that I'm writing in this notation because you'll see this more and more. This notation is like, you can think of like a linear, this is describing like a line, and this W and this X are actually like, if you imagine this more like vectors. So this W, it could be like well, it'd be like an actual number. So this would simplify out to, if I had different parts, you might have something that looks like, come on, there we go, line. So this might, for example, look out like W1, where W1's a number, X1, right, or like X, plus W2 is another number, times like Y, right? I guess if I got rid of this part. Sometimes you'll see this X1, because we can go in general dimensions, plus this number B is equal to like 0, okay? And essentially this is like, if you look at it, this is basically just an equation for a line. That's essentially what we're doing. If we had more variables, if I had like X1, X2, X3, like X, Y, and Z, that would be a three-dimensional plane, or not, sorry, three-dimensional plane. It'd be a 2D plane within the 3D space. And then we could keep adding more and more X1s and X2s and make it larger and larger. Essentially, we're saying this is our actual, our model right there. That's kind of like the thing going through. This is just our notation we use. And the real reason why we use it is something called a Fourier perceptron. This is actually, if you look into this is actually a perceptron model. Perception, oh, I spelled this wrong. Perceptron. I think it's perceptron. I don't know if that's look right. It's either E first or R first. I'm no good speller, but a perceptron model. I'm gonna look this up because it'll kill me otherwise. It is PER. Dang. Okay, that was close. Okay, so perceptron, not perceptron. Okay, But this is actually just another way of just saying a linear line. Hey, hello dog. But that's essentially what we're trying to build here. So this WB equals 0, WB plus 1, WB equals 2. You could also have WB plus, sorry, equals -1, -2, and stuff like that. Sorry, my dog is like needy sometimes. But those are basically just saying parallel lines with a different kind of like factor. So you can imagine, is that like maybe, hi, thank you. The WX plus B equals 0 is this blue line. This WB equals 1 is maybe like this orange line on the left side, and then equals 2 might be this red line. So it's kind of like parallel lines going up and up and up, and then going in the opposite direction, it's going negative, 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 negative. Okay, so that's important because then we can use those models actually being able to predict, or not predict, but basically calculate the error. So I'm not going to go into the full calculation. The curriculum does do that, but just know that essentially by using these equations, essentially by making each of these lines different values, we can calculate the error for one, the classification, how many actually cross through over onto the other side, and then two, actual margin. And the reason why we do the margin here is because what we'll actually do is we'll say, going in from that little diagram up here, we'll actually count, let's say from this red margin here, we'll actually say, okay, everything to the right here, okay? And basically we will increase the error as we go further and further to the right. So this is the way we consider large points over here. And then going on this side, we'll actually count the error on this side. So we'll actually use this to say, if there's, even if they're, let's say, purple points right inside here, those will still be part of our error, and they'll actually count towards our margin error itself. These points would normally not be classified as errors because our model fits fine. But because we're using it at support vector machine, we're trying to encourage using that margin more and more. Okay, so I'm just going to quickly go through this. Forgive me if it feels a little like wait, what? But basically you can see here is this is our error that's going to be the margin error, and saying, hey, okay, we're taking this norm, basically saying basically how far is it from like each error that's there. So if you imagine in the margin, if there was like a purple one right here where my cursor is, okay, that would be a margin, let's say, of like equals 1. So it'd be 1 squared, but then we also would have it along the x-axis and the y-axis. So you can have it for multiple dimensions. In reality, you wouldn't be calculating this by hand, essentially, but you know, it's important to know that basically as they go up and up and up, basically your errors become less and less, become more and more important in that way. And then this m right here is representing the margin. So this is actually how we define it. So once we figure out what this w squared is, we can actually say that's the error. And then actually defining what our margin is, we can use that same idea here, okay, to say, okay, this guy right here, and this should be squared. I'm sorry, I just realized that should actually be squared. But the important part is that the error is basically squaring it. So the error will increase, 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 right? So like you can imagine if we have very, very large distances in there. So basically if you imagine it's like our yellow point's way off inside where we say it's supposed to be purple, then that's going to be a big, you know, error. Versus if it's very close, it's going to be relatively small. And then this margin right here basically is the distance between those two lines. So you imagine from this orange line to this orange line, and this red line to this red line. And that will basically define our margin. So it's kind of nice that you have now an automatic way to increase and decrease that margin and figure those parts out and actually quantify this. And so just know that this basically having a larger margin actually will decrease our error in this way. So they're kind of like, as you increase and decrease that margin, you actually, using the same data points and the same exact like blue line, you'll actually, what's it called? By decreasing the margin, you actually will increase your error. And the reason why is because we start counting as like, this is our first like line right here. This red line is our second line, and then going further and further out. So it increases much quicker. So if you imagine like, if this is, it's not completely to scale, but if you imagine like, this is our, let's say, oops, I'm trying to draw here, there we go. B equals 1. is this line right here. Well, the next line would be like b equals 2. And then if I had like a third line right here, this would be b equals 3. Okay, and the next line right here would be b equals 4. So basically, those errors going from here outward, those errors are going to increase. Versus if I had just in red, then red would say, okay, this is b equals 1, and then maybe like the red one's right here, this would be b equals 2. So it actually will increase the error if we have small margins, and if we have larger margins, we'll actually get a smaller error. Okay, and that's kind of how we are able to encourage bigger margins, essentially. With gradient descent, we're going to try to optimize that error to be as small possible, and that will basically encourage the gradient descent to want to have large margins that still are have low error. Okay. Hopefully that kind of gives you a little bit of idea versus just it being mathematical. But if you wanted to go mathematical, basically you could just see this inverse relationship and say, oh, we want to minimize the error. Well, the error is related to w squared, but the margin is inversely proportional. So if you decrease this w, m will get bigger. And if you increase w, m will get smaller. But then if you increase w, your error will be larger. So basically it comes in the fact that if you make your margin smaller, it'll make your error bigger. Okay. Okay. Give me a thumbs up if that sounds fine. Thumbs sideways, you're like, I don't know. Thumbs down, you're like, no, I'm completely lost. Okay, I see some thumb up there. Okay. All right, that was, to be honest, that was a little confusing, but hopefully that gives you a little idea of where this mathematics is coming from. Okay. And again, gradient descent is just used to minimize. I decided not to put anything on here because I didn't want to go into that whole process. But I think the curriculum actually shows how to do this by scratch kind of deal. Okay. So this kind of leads us into a hyperparameter called C, right? And literally it's just called C. I don't even know like if there's a reason why we had C, but basically it's a constant. It's a number that allows us to say, which one do we care about more? Do we care about more classification, or do we care about more about error, the margin error? So kind of a question here is that you see, basically we have C, it's defined so we get this error total. It's just equal to C times the error classification. And so C is some kind of number that we give it, plus the error margin. So let me ask you guys, if we were to make C larger, what happens? Basically, what errors do we care about more when we make C larger?
The error classification.
Right, yeah, if we make C bigger, right, error classification is gonna matter more, right? Which means what's going to happen there is the error going to go down or go up.
I'm going to just guess that it goes down.
Okay, yeah, it's okay. This is where like the mathematics kind of like can be a little intimidating, right? But you're right about it saying, if we say increase C, we're saying, oh, small little errors in the classification will matter more, which basically means when we say matter more, it'll give a bigger error. So actually increasing C says, oh, we want classification errors to matter more. So if a classification error, let's say the error is some like 0.1. Well, if we had a C of like 100, right? Now all of a sudden that 0.1 error that would have been like a very small error total, now it matters like, let's say, what's that? I said 100. So it'd be like 10 times. So it'd be like, oh, your error total now is 10 versus like a small little 0.1. So essentially what it means is our classification matters more, and it'll give us, that's funny, I wrote this wrong. Big C will give us a smaller C. That doesn't make any sense. But it should basically mean that a bigger C, which should provide us with a smaller margin. Basically, we care more about making sure it's classified versus trying to get the margin error proper. So this will overpower, and basically gradient descent will tend to optimize for this classification error. Okay. And so that's it, kind of like gives you, hopefully gives you an idea of why, like honestly, the hyperparameter, if you just like read it on like, what's it called? Like an sklearn, it might say something along the lines of like, oh, if you increase C, classification error matters more, therefore margins will be smaller. But this gives you like a mathematical reason why that happens. And essentially it just means we're just multiplying the error classification by some number here. Okay. So cool, that's kind of like all the theory kind of going through it. So nice to see some code. So this actually, I think this is my own code. But basically, sklearn has a SVM, which is kind of confusing, support vector machines, and then you see SVC. It's support vector classifier. So that's essentially what it's doing. And it's using also the C parameter. So there's a few parameters in here, kernel, which we'll talk about with the kernel trick, but there are also things like gamma, which we'll also talk about the kernel trick. And there's some things like degree where we can change. Again, these are all like, these parameters right here are all dependent on the actual kernel itself. But the one I wanted to talk about is actually using the C. So basically that C parameter allows us, oh, there it is, the very first one. Basically, it's the penalty parameter of the error term, basically saying how much do we actually care about the classification. And you can see here the default is 1, which means that basically error in the classification error in the margin error are essentially treated equally. Okay, so we're actually just run this. So you can see here, basically this is going to create a classifier. So you can see here, just importing it through SVC, I have classifier. So I have a classifier. It's all set and ready to go. It's ready to be trained. Okay, it's ready to learn. So I'm just going to use the same data I had before. So just kind of show you a little bit what this looks like. You can see here is that basically using the same iris data, basically making it so it's 2 classes. Note if I got rid of this part right here, I'll just show you guys what it looks like without this. So you guys are like, why did I do this? You can see here, then we have some green mixed in. By making it nice and simple, where it's like very definite, clear, you know, what should be it, but you can have some mixed in. But anyway, so we have our nice model right here. And now what we want to do is want to train it. So what I have here is I'm only using the first 2 features of this data set. So I'm only using the first column and the second column, 0 and 1. And so now we can actually fit it. So this right here will take in basically all the features. So note this is a NumPy array. So if you were to look at this by itself, you can see that this guy right here is basically just, this is each data point, and that's our first column here, our second column here, and then we're going to feed that in. So that's what this part is. And then the iris targets, basically it's going to represent you know, what should it be labeled as. And you can see it basically will be 0 or 1. And you can see here it's just labeled in this way. Okay, so I basically feed this data in here. Note that I just put this gamma equals auto, but I didn't have to do that. I just made it so it's optimized a little bit better. I go ahead and fit it, and basically it's done. It figured out the way it's going to classify it. So to use this classifier to say, hey, what do I want to do? What you would do now is you would basically say you get a new point. Let's say I'm going to use this in, I'll use green. Yeah, we'll use light green. Okay, so imagine if I say, okay, I get a point at 5, 5, 2.5. So I get a point like right here. Oops, I should actually be able to draw. There we go. If I get a point right here, okay, what should that be classified at? Yellow or purple?
Yellow.
Yellow, right? Yeah, right. And then you can see my next one here. I have 5.5 and 3.5. That would be right about here. Okay. What should that be classified as?
Purple.
Purple, right? Yeah. It's no trick questions, right? So pretty straightforward. So we'll, hopefully, if our classifier did a good job, we'll see this will print out, I think 0, oh no, sorry, 1 is yellow. So we should hopefully see 1. Cross your fingers, right? Not good. So I figured it out that basically I put in this point 5.5, 2.5, which would be right about here. I got shifted a little bit, but that would be yellow. And then this one right here, which we said should be purple, should give us 0. And gives us 0. Cool. So this is kind of like gives you kind of some quick, you know, going through. If you wanted to go like plot this out, you could possibly like put a bunch of like, you know, points and stuff like that, which I'm kind of tempted to do right now, but maybe we'll save that at the end. But you could potentially like do a bunch of data points and say, go ahead and tell me what the classification should be, and you can plot those out. Yeah, so that's essentially how you could feed it in. Now, note that I did this with 2 dimensions. You could easily make this for 4 features or 5 features or whatever dimensional features you're looking at. Okay. Any questions on this? Yeah.
I don't know if this is possible, but with the whole prediction stuff, it's kind of like it's looking at, well, there's an imaginary line, and whatever's above it, it predicts purple. Whatever's below it predicts yellow. Now, what if it happens to fall on the imaginary line? Exactly. Is that ever possible?
Yeah, it can. And that's where it still has to, computers have to decide, because it's discrete, they have to, at some level, have to decide when it's this level versus the other level. I don't know if it's like like it's one of those things like, you know, how exact can you get? But yeah, it could fall on the line or close to the line, and basically it's going to have to define basically through estimation probably is like whatever's closest. But yeah, it could fall almost directly on the line. And you might just have something that's going to still give you, it still has to give you a 0, 1, right?
Mhm.
So it just depends on like, you know, how it's defined there. Yeah, good one. Cool. Yeah. Any questions you guys have? Go for it. No? Sound pretty good?
I have one question. On the margins again, the margin of errors, you say that there's could be, well, multiple margins of errors, levels of margins, I mean.
Right. So like we were talking about like the WX plus B equals 0 equals 1. That's how you're talking about?
Yeah. Can the levels be different as in the size of each level? Like, or is it the size of each level always the same?
Oh yeah, this is just more like representing the margin. It could be like, when I say 1, it's for us to like more easily draw those lines out. But like if you had a point that was like right here, that error might be like 1.3 or 1.32 or something like that. It's basically just saying how many margins is it away from that line. Does that make sense?
Yeah.
Okay. Yeah.
Oh,
So
yeah. Okay.
Yes, it's kind of like, you know, can almost measure like standard deviation. Like we say standard deviation, but you can be multiple standard deviations away from the mean. That's kind of like, in my mind, that's kind of what I imagine.
So it's not like all data points that fall within level 1 are this, all fall with level 2 are this. It's not like that. It's just you're gonna get the exact number.
Yeah, exactly.
Okay.
Yeah, I mostly did this because like if I were to do this well and I was a good artist, I could like make a gradient that goes from like really yellow, like right here, and then like as it went outward, like fade to like white. It's basically representing that the error matters less and less and less as it goes kind of further out. So like those, or I guess I could do the opposite where it's really white, where it's a low number, and then as it goes like, you know, further out, it gets deeper yellow, so that then like a higher value.
Oh, I see.
Cool.